Hello everyone, this chapter talks about technical principles of HDFS. After this course, we'll be able to know HDFS application scenarios, HDFS system architecture, and some key features. HDFS is a Hadoop Distributed File System. So what is a file system? Well, file system is a way of storing and organizing computer data to facilitate data access and query. In a dictionary, we can quickly search the word from dictionary body based on the character index. So file system is kind of similar. File name is used for locating a file in the file system, and metadata records file attributes such as file name, length, user group, and location. Data block here is the smallest file storage unit, so we can find the data block based on the file name and metadata. Unlike other distributed file systems, HDFS is highly fault-tolerant, which resolves hardware reliability problems. Since HDFS includes a large number of commodity hardware, failure of components is frequent. Therefore, high fault tolerance makes sure that we can still access the file system if one node fails. It also provides high throughput access to application data and is suitable for applications that have large datasets. And it supports TB and PB level data storage. So HDFS is suitable for large file storage and streaming data access. Here, streaming data access means that access to data files is handled in a streaming manner. HDFS is built around the idea that the most efficient data processing pattern is a write once, read many times pattern. A dataset is typically generated or copied from source, and then various analyses are performed on that dataset over time. Each analysis will involve a large proportion of the dataset, or maybe the whole dataset. So the time to read the whole dataset is more important than the latency in reading the first record. However, HDFS is inapplicable to the following scenarios. Store massive small files. Actually, metadata of a file system is loaded to memory of a specific server called name node. So the number of files that can be stored in the system is restricted by name node memory capacity. The directory and data block of a file each is about 150 bytes in size. If there are 1,000,000 files with each occupying a data block, at least 300 MB memory is required. If there are 1 billion files, the required memory will be huge. Second is random write. Files in HDFS may be written to by a single writer. Writes are always made at the end of the file. There is no support for multiple writers or for arbitrary modifications in the file. And low delay rate. Applications that require low latency access to data in tens of milliseconds range do not work well with HDFS. Remember, HDFS is optimized for delivering a high throughput of data, and this may bring high delay. So in conclusion, HDFS is a distributed file system for managing files on multiple independent physical servers. In reality, for example, HDFS can be used for storing website user behavior data, or ecosystem data, or meteorological data. Then let's take a look at the position of HDFS in Fusion Insight HD. Based on this figure, we can see that HDFS works as the Hadoop data storage infrastructure with high fault tolerance, high throughput, and it can store large files, so it's on the bottom of the Hadoop architecture. Then let's take a look at HDFS system architecture. The HDFS architecture consists of three parts: name node, data node, and client. Name node is used to store and generate metadata of the file system. It also knows the data nodes on which all the blocks for a given file are located. A HDFS runs only one name node instance. Data node is used to store actual data and report back to the name node with data blocks under its management. They also perform operations such as block create, delete, and replicate according to the instructions of the name node. A HDFS can run multiple data node instances. And inside of a data node, there are blocks, which are the minimum amount of data that HDFS can read or write. The file in a file system will be divided into one or more segments and stored in individual data nodes. So these file segments are called as blocks. The default block size is 128 MB, but it can be changed in HDFS configuration according to the need. The client allows services to access HDFS and returns data obtained from name node and data node to services. A HDFS runs multiple client instances. Here shows the process of writing data to HDFS. So first, a service application invokes an API provided by the HDFS client to request for data writing. The HDFS client creates the file by calling the create method of distributed file system. Then, distributed file system sends an RPC request to the name node to create a new file in the namespace. And the distributed file system also returns FS data output stream to the client for writing data into it. After receiving the service data, the HDFS client obtains the data block number and the location from name node, connects to data nodes, and establishes a pipeline of data nodes where data needs to be written to. Then, the HDFS client uses the proprietary protocol to write data to data node 1 and copy the data from data node 1 to data node 2 and data node 2 to data node 3. After data writing is complete, the data nodes send a confirmation message back to the HDFS client. After all data writing is confirmed, the service invokes the HDFS client to close the file and connect to the name node to confirm that the data writing is complete. The process of reading data is similar but much more easier. A service application invokes an API provided by the HDFS client to open a file. The HDFS client opens a file by calling the open method of distributed file system object. Then, distributed file system sends an RPC request to the name node to locate the blocks of a file to be read. Then, distributed file system returns FS data input stream to the HDFS client for the client to read data. The HDFS client connects to multiple data nodes according to the information obtained from the name node. After data reading is complete, the service application invokes the close API to close the connection. Next, let's see some key features of HDFS. There are multiple key features of HDFS architecture like federation storage, data storage policy, HA, multiple access modes, space reclamation, name node, data node in masters and slave mode, unified file system namespace, data replication, metadata persistence, and robustness. First, HA, short for high availability. The HDFS high availability is mainly reflected in active standby name node elected by Zookeeper to solve name node failure problems. The active name node provides services, and the standby name node backs up metadata as a hot spare. HDFS uses journal node to store edit log, which records user operations generated by active name node. Standby name node loads edit log on journal node to synchronize metadata so that the standby name node can take over the job very quickly if the active name node fails. In this case, the whole file system will not be affected. Zookeeper is mainly used to store status files and active or standby status information. ZKFC, which is Zookeeper Failover Controller, is used for monitoring the active or standby status of NameNode. The process of metadata persistence is as follows. First, the standby name node informs the active name node of generating a new log file called editlog.new, so that the active name node can continue recording logs to the editlog.new file, and the standby name node can obtain the old editlog from journal node and download the FS image, which stores the file mirroring periodically from the active name node. The standby name node merges these two and generates a new metadata file called fsimage.ckpt. Then, the standby name node uploads the new metadata file to the active name node. The name of the file is changed to fsimage to override the original fsimage file, and the editlog.new file is also renamed as editlog. Name node triggers the metadata persistence operation every hour or when the capacity of editlog is 64 MB. We know that the name node keeps a reference to every file and block in the file system in memory, which means that on very large clusters with many files, memory becomes the limiting factor for scaling. So, HDFS federation allows a cluster to scale by adding name nodes. Each one manages a portion of the file system namespace. For example, one name node might manage all the files rooted under the user directory, and the second name node might handle files under the database directory. And each name node has its corresponding standby name node. Under federation, each name node manages a namespace volume, which is made up of the metadata for the namespace, and a block pool containing all the blocks for the files in the namespace. We've mentioned before that HDFS is highly fault-tolerant. This feature is accomplished by data replication mechanism. HDFS replicates file blocks and stores in different data nodes. An application can specify the number of replicas of a file at the time it's created, and this number can be changed anytime after that. Optimizing replica placement makes HDFS unique from most other distributed file systems, and it's facilitated by an intelligent replica placement policy. which is to place the first replica on the same node as the client. The second replica is placed on a remote rack. The third replica is placed on another rack if the first two replicas are placed on the same rack. Otherwise, the third replica and the first replica are placed on different nodes in the same rack. Other replicas are randomly placed on the cluster. And by default, the HDFS name node automatically selects data nodes to store data replicas. But we can configure the way of HDFS data storage based on the actual needs. There are three common scenarios in practice: store data in different storage devices, store data with labels, and store data in highly reliable node groups. So first, store data in different storage devices. The HDFS layered storage architecture provides four types of storage devices: RAM disk, archive, and SSD. We can make storage policies for different scenarios by combining these four types of storage devices. Take the 15 lazy persist policy as an example. Assumed that the configured number of block replicas is 3, the first replica is written to RAM disk and the other two are written to disk. As an alternative, if the first replica fails to be written to RAM disk, then the first replica is written to the storage type specified by alternative storage policy, which is written to disk. And if the other two fail to be written to disk, then the other two replicas are written to the storage type specified by alternative replica storage policy of other replicas, which is also disk. Second, store data with tags. Users can flexibly configure HDFS data block policies based on service requirements and data features. Set one tag for each HDFS directory and one or more tags for each data node. In this case, we can specify the data nodes for file data storage. For example, data in the HBase directory is stored in data node A, B, and D. Third, force to store key data in highly reliable nodes. In practice, key data needs to be stored in highly reliable nodes based on service requirements. The system can force to save data to specified node groups by modifying data node storage policies. In this policy, the first replica is written to a mandatory rack group, group 2 for example. If there are no available nodes in this mandatory rack group, data write fails. The second replica is written to a random node from a non-mandatory rack group, where a local client is located. If the local client is located in the mandatory rack group, then the second replica is written to a node from other rack groups, and the third replica is written to a node of other rack groups. These replicas need to be stored in different rack groups. If the number of replicas is greater than that of available rack groups, extra replicas are stored in random rack groups. For example, for file 1, the number of replica is 1, so it's written to node 3 of mandatory rack group. And for file 2, the number of replicas is 3, so the first replica is written to node 3 in the mandatory rack group, and the other two are written to node 2 and node 8 respectively in rack group 1 and rack group 4. Co-location means to store associated data or data that is going to be associated on the same storage node. For example, assume that file A and file D are going to be associated with each other, which involves massive network switch, costing a lot of internet and I/O resources. So in this case, HDFS implements file-level co-location. That is, the blocks of multiple associated files are distributed on the same storage node. In this way, which facilitates quick file access and avoids high costs of data migration, greatly reduce the resource consumption. In order to assure data integrity, HDFS has the following methods in case of failure of each component. First, data node sends heartbeat messages to the name node periodically to report the data status, and the name node checks whether the data blocks are completely reported. If the data blocks are not reported because the disk of the data node is damaged, the name node initiates the replica reconstruction to recover the lost replica. HDFS also has a data balance mechanism which ensures the even distribution of data among all data nodes. Besides, metadata in HDFS is stored on both active and standby name nodes, and data can be recovered in time with the snapshot mechanism if a misoperation occurs. HDFS also can prevent fault spreading with security mode. Data in HDFS becomes read-only, and operations such as create or delete a file will fail. HDFS cluster exits the security mode after the fault is resolved and data recovered. HDFS also has some other features, like it presents itself as a unified file system. It supports recycle bin mechanism, which means that files can be recovered if accidentally deleted, and data is stored by blocks in HDFS. Besides, data can be accessed through Java APIs, HTTP, or shell commands. Here shows some common shell commands, which are kind of similar to the commands in Linux. So this chapter mainly talks about HDFS, including its basic concepts, application scenarios, technical architecture, and some key features. Okay, that's all for HDFS. Thank you.